in person. It's been a while. So it's great to interact with human beings 3D. I'm going to be talking about discrete gradient vector fields and the connection with rooted forest for simplicial complexes. This is joint work with former student Andrew Tawfeek, who is now a grad student at University of Washington, but he worked with me and also with Alejandro for his senior thesis at Amherst. I'm not assuming any familiarity whatsoever with the topic, so I'm going to start slow, and I apologize if the beginning of the talk is a bit slow, but for the exercise, it has 4 steps, but please don't get scared. If we don't manage to finish the example, it's totally okay. But the idea is we will study the one-dimensional case of the talk. So when you have simplicial complexes, a natural example is graphs. So we will study a very simple graph that is K3, just a cycle. And we will compute the graph homology associated to it. So I will explain in a second how to do that. We will also consider 2 possible Laplacians. So there are some matrices that are the discrete analog of what you learn about the Laplace operator in calculus, say. And then we will see something that looks like the Hodge theorem. So the Laplacian knows about the topology of the graph. And we will construct 2, well, hopefully 2, maybe more. We'll see if we have time. Discrete Morse functions, and verify something that is called Morse inequalities. So in continuous Morse theory, there's a relationship between the Betti numbers of a manifold and the number of critical points of a Morse function. So we will see that in the context of graphs. And then we will have a visualization of these Morse functions in terms of vector fields. And I think that will help us to motivate the content of the talk. We want to count them. So a natural question is, well, you have Morse functions defined on simplicial complexes, how many of them are there? And the idea that I want to convey today is that you can use this vector field representation, these gradient vector fields, and you want to classify how many you have. And that's related to the Laplacian. All right. So please stop me if you have any questions. But we will start with this graph. This is familiar to everybody. 3 vertices, 3 edges. But for the sake of the computation, I need to choose an orientation. This is going to be a directed graph. And because I wanted to make it a little bit more interesting, it's not going to be the usual clockwise or anti-clockwise. It's going to be this one. So 2 is kind of preferred in this orientation. So so the first thing is we will compute graph homology for this graph. So it's going to be a very small chain complex in which we will have here. Oh, I think there are questions or.
Yeah, I'm asking if we can see.
Oh, okay. Okay. So we will consider here r to the 3, that is going to be the edges, and here we will put r to the 3, that is spanned by the vertices, and then we want an operator that goes from here to here, and this is going to be the incidence. So we will use for our boundary operator the incidence matrix. And because I was told that this pre-talk is more like something that we can work together, I need all of us to work together. And you should tell me what is the incidence matrix for this graph and that orientation. I can help. So there will be here A, B, and C, the edges, here 1, 2, 3, the vertices, and then we just have to give -1 when the edge starts at a given vertex, 1 if we end at that vertex, and 0 otherwise. So what do we get?
First column should be like 0, 1, maybe 1.
Thank you. Next. I can help. I know this one. So for the second column, we end at 1, so we should put a 1 here, and we start at 3. And for this one, we start we start here, and then we end here. Okay. So so this is the incidence for. So this is going to be the boundary operator here. So the homology H0 of K3 is going to be defined. In this case, this will be the 0 operator and the 0 operator here. So it's going to be the kernel of, so if we do it for going to be kernel mod image. So if we do it for here for vertices, so it's going to be the so here this is the kernel of the boundary, so the incidence modulo the image. And someone maybe quickly could tell me what is the dimension of the kernel. I know that this is just linear algebra, but if you look at the at that matrix and you compute the kernel, what do we get? What dimension do we get? It's one dimensional. And what if we do the same thing for the other direction? So we are over here. So now we take the kernel of 0 modulo the image of this one. That will take a little bit long, but longer than just finding the kernel. But a quick computation will tell us that we also get R. So the interesting thing here is that knowing the kernel and the image of the incidence tells me about the topology of the graph. We have one connected component and we have one cycle. And that generalizes to simplicial complexes. So that's item 1 of our computation. Now, Laplacians. There's no Laplacians here, but one would like to construct an operator that starts and ends with edges and starts and ends with verts. So there are 2 of them. Yes.
Okay, so the R1, so the H0, the one there gives me the number of components.
Yeah, this is B0, that is the number of components, and this is B1, that is the number of cycles. Sure. So now we want to construct an operator that goes from here to here and from here to here, but we want to use the incidence. So there's a way to do it. That is, if you can go from here to here using the incidence, you can take its dual. That goes now the dual map, and then you compose and pre-compose with that, and you can do that in 2 different ways. So if you do it here, that means you apply first I and then return with I dual. Then you have one Laplacian, and here you have another Laplacian. And let me just differentiate them. I will call this one delta 0 and delta 1. Okay. Is it clear how we are going to construct them?
So these are square matrices whose size is either the size of the number of the vertices or
Yes,
the number of the
exactly. And depends in which order you put the incidence. One question is, are these the same matrix? No, because it could be that you have a graph that doesn't match. So in general are different. In this case, they match the numbers, but that doesn't mean that they have to be the same. So can someone, this is kind of speed dial linear algebra, but can you guess what is the Laplacian for this particular choice of the incidence?
Sorry, I have a question. So
Yes.
So delta one is that obtained by taking, sorry,
Oh, yeah.
the obtained by
So
taking-
delta one, we are in edges. So we are here. So you apply first I, so that's going to the right, and then I dual. Okay. That is the transpose, and then delta zero is the other way. So I know the answer to both, but I think that's cheating. But maybe we can try together. So it's an interesting thing that in both the diagonal is 2. If you compute, or let me see which one is the one that I want. The one for vertices, so delta 1. So if you compute this one, you will get this, all negative ones. And this one, that is interesting, this one depends on the orientation. So if I would have told you a different orientation, delta 0 will change, but delta 1 won't change. Delta 1 is independent on orientation, delta 0 is dependent. And this one, I have to believe in my memory, is 1, 1, negative 1. So there is a change between these two Laplacians. All right. Are there any questions?
Yeah, if you wanted to generalize to higher dimensions, why wouldn't you just keep doing del star? So you get to 0 for delta 0.
Right.
I would imagine it would just be del star going to the 0.
And then come back. Yes.
Yeah. So not.
Oh, you keep one. Well,
Yeah, you keep going to the right and then you come back to the left.
right. So yes. So you could actually do that. And in terms of, for example, the eigenvalues or the spectrum of these two things, they are definitely the same thing. So you could define the other Laplacian to be just following the same, like the same direction.
If I went to the right and then back to the left, I get a 3 by 3 0 matrix. Right?
Oh, yes, you're right. So we don't want. So there's one direction when you finish the complex that you don't want to get a trivial Laplacian. So for the last one, for example, there's the you try to avoid having the 0 and the trivial Laplacian, and that can be avoided by just using the other direction. So in general, this is part of something that is called the Hodge Laplacian, in which you actually take both. You go to the right and to the left. So it's very like democratic. But in this purpose, we just don't want like degeneracies. Yeah. Thank you. And then now that we are talking about this Hodge decomposition theorem, so there is an indication of this Hodge theorem that tells me that if I compute the kernel of these matrices, they are actually isomorphic to the homology. So it turns out in this particular case that if you do the computation of the kernel for these two matrices, you will get 1. It's a one-dimensional thing. But this is a more general construction for higher dimensions, in which you can compute topological invariance using the kernel of the Laplacian. So the Laplacian knows about the topology. So these are items 1 and 2 of our small exercise. I don't know how much time do we have.
7 more minutes.
7 more minutes. Okay. So I can try to. And is there a break between?
Yeah, we have a break later.
Okay. Good. So maybe we can go and move on to finding some examples of discrete Morse functions, and see. At the beginning, it's just going to be an intuitive way to produce Morse functions, and during the talk we will see a more detailed definition of what a Morse function is. So I will give you 2 examples of Morse functions, and this will model what a Morse function is for a manifold. If you have seen that before, a Morse function is something that looks like the height function. So you just put, for example, a torus, you just put it vertically, and the idea is that you don't want you want isolated critical points. So you don't want things that look like the roof of a house. So you want things that that the critical points are well behaved. So I will give you 2 examples. One is more trivial than the other. So let me introduce you to the first discrete Morse function on K3, and I will give you another one. So a discrete Morse function is going to be a function that you have, so numbers associated to vertices and edges for a graph. They have to satisfy certain property that I will make more precise in the talk with a more formal definition. But we could see here that whenever there's a change in dimension, there seems to be a change in the value, right? So for example, here there's a lot of change, and here, well, it's a little bit more controlled. But still, I've not given you a precise definition of what a Morse function is. But maybe we could see here, and maybe you can tell me, and we can work together. What do you think are the critical vertices or the critical cells for this Morse function? And by critical meaning like local max or local min. Which one will have more critical cells? This one or this one? This one, like how many? How many critical cells? 6, yes, like everything is critical here. Because whenever if you're here, then you are a local min. And if you are in the edge, you're a local max. And you can do that for it. So you have 6 critical cells, 3 critical vertices, 3 critical edges. How about here? What are critical? What seems critical? 0 and 2. So this is critical and this is critical. Nice. Yes. What can I do with those numbers? So is there anything connecting this number of critical cells with what I just explained at the beginning? Like those Betty numbers, for example.
Why are you not treating the ones as local maxima?
Well, that's a good question because these ones maybe?
Yeah,
Oh, you see, because there's a vertex here that has the same value.
but
So
it's still a local maxima. It does have to be a strict maximum.
Yes. So yeah, it's like if you were to draw like gradients, like vector fields, you have to move in that direction. Like here, there's no like place to move. So here, yeah. So here I would represent this if I were to draw a vector field like this, because you go from 1 to 0. So here we have C0, that is the number of critical vertices, is 1. And C1, that is the number of critical edges, is 1. C0 is 3, and C1 is 3. Well, it turns out, and this is what is called discrete Morse inequalities, these numbers are always bounded from below by topological information. So the number of connected components is always a lower bound for the number of critical vertices, and the number of cycles is a lower bound for the number of critical edges. And no matter what Morse function you use. And this one is like the best one because it's actually tight. It gives you the equality. So this one is the one that should be called the height function. Like this is the one that topologists would appreciate more because this one actually realizes the Morse complex. So here we have like extra critical cells.
Every graph has a tight one.
Every graph has a type one.
Higher dimensions too. Probably not.
Probably yes. There are some conditions for the simplicial complex to have a type 1. Yes, that is true. But there's always so you can always have a good. You have one that is the closest to the type 1. That is, you can construct the spanning tree. So every graph has a spanning tree, and every simplicial complex has a spanning forest. And then you can define what you do here. So you can define the depth Morse function for a tree that is 0 at the level 1 at the 0 level, and then keep going up, and then you kind of take the closure of this function, and that gives you like a tight Morse function for a simplicial complex. So you can do that always for graphs, and then for simplicial complexes is kind of tied to the existence of these Morse functions on forests. All right. So, and now I think, and that will end the pre-talk is, now the question is, how many do you think we have? So if I give you K3, I want to count how many discrete Morse functions we have. Of course, it won't be like counting the possible values on the vertices or edges because there are infinitely many. But you could imagine that what I want to do is count the number of gradient flows. So the number of ways that I can kind of go from critical to critical. And that's finite, that should be countable. And that's the content of the talk. So it's how many of those gradient vector fields we have. Any questions?
I haven't seen one. I'm sorry. Maybe you talked about it. One of the ways to realize the H vector in this polytope is to scan it with a hyperplane.
Yes.
And at this point, we record the number of exterior of edges of course, right?
Yes.
So this looks a little bit similar, obviously, with a Morse function.
Yes.
I was wondering if there's an analog of that quantity, the number of exterior edges, all of that.
That is, and I think that's something that people have studied. That is basically algebraic Morse theory. That is basically trying to do what you do for simplicial complexes, but for example, for polytopes that are a little bit more rigid. So there are some kind of conjectures that like that vector corresponds to the vector that people call like the Poincaré vector, or just like going from critical cells to critical cells using this kind of gradient as kind of like the differential. So I think I'm not so sure if there has been a full understanding of this connection between those two, but definitely, yeah, people have studied that, like connections between like polytopes as certain realizations of this kind of simplicial or discrete version.
If there are analogs of this vector, do they have the nice property that the H vector has sometimes, like in modalities?
Oh, that's a good question. I don't know. I feel like the properties that you have here are more like of topological nature. So you could talk about, for example, the Euler characteristic, or if you want, people have studied discrete Morse theory. If you want to show that a certain discrete space is contracted. So yeah, I don't know if that fully answers, because it seems to me that what you know for polytopes is yeah.
No, I was being unfair. You gave me a perfect answer, but then I liked it, so I asked even more.
No. Yeah, I would love to explore the world of polytopes. There are experts here that could tell more about that.
Is this discrete Morse theory algebraic topology or differential topology? Like if I have two spaces are homotopy equivalent, and then I look at their simplicial complexes, am I not going to? They're going to have to all the same discrete Morse data. It's different because Morse theory is for smooth.
Right.
Smooth
Right. I think that's a fair point. So what in my understanding of what Forman did is he wanted to have a discrete version of the Morse complex that appears in differential topology, and mimicking basically the whole construction of Morse, like defining the Morse complex in a similar way as like critical cells. And what he proved, like the main theorem in discrete Morse theory, is that if you have any simplicial complex, there is a way, something that looks like a deformation retract to the Morse complex, like the discrete Morse complex. So I would call it that it is actually differential topology. Like
you said deformation retract, so that sounds like algebraic topology. Or throwing away all the other.
Right. I feel like to be fair, in the field of Morse theory, discrete Morse theory, people talk about algebraic Morse theory and like something that is like differential Morse theory. And I'm guessing this is a difference between like the thing that you're mentioning, something at the level of like the differential topology and the algebraic. But definitely there is a discrete Morse theory version of deformation retract that you can do for simplices. Like I think the example for that is
a simple homotopy equivalence.
Yeah, that's a good question. I think it's a bit more subtle. Than, like in the example, like one-dimensional, I think they should be like the same. Like the one that I wanted to describe is if you have a tree or something, you can always kind of contract one of those.
That's a simple homotopy equivalence.
So that, yes, so I would say that that fits with that one.
I have a sillier question, I think, but is counting the possible vector fields the same as calculate or counting the acyclic orientations? Of the
Yes, yes, it's exactly the same thing. And then you do it, you extend this condition for higher dimensions. So it's and I think that's the idea of the proof of the theorem goes through like people have proven how to count things on the number of acyclic functions. So you can show that if you have a Morse function, you cannot have this. This is bad. So we avoid that. Yeah.
I think we'll resume a little bit in maybe 3 minutes. We're going to take out the word. So I'll close the recording. We'll resume it.
Yeah, you looked at any.
Am I well located in the? So do people hear fine?
I can ask. Yeah, so, yeah. If you wouldn't say here, yes.
Okay.
Okay, so it's
Sure.
Yes, yeah, there.
Oh, okay.
You put the cover of your pen,
Yeah.
cover again. So, okay, welcome everyone. So we're very happy to have Contreras Palacios from Amherst College, who is celebrating today the bicentennial. And he's going to talk today about discrete gradient vector fields and root forests of simplicial complex.
So yeah, thank you. I'm very excited to be here. There's going to be a party afterwards, and it happens every 200 years. So I apologize if I have to run after the talk. All right. So so I'm going to be talking about this idea of using Morse theory to do a counting problem. That is counting the number of gradient vector fields on a simplicial complex. And this is related to generalization of the graph Laplacian. So there is some content that relates to graph theory in this talk. And just to remind you what we just did in the pre-talk, we did with one particular kind of instance of this that is just a graph, a one-dimensional simplicial complex. It was K3. We saw that you can produce something called the graph homology. You can produce some sort of invariance, number of cycles, number of connected components, and that is related to critical cells for a Morse function. We also saw something that is called the Hodge theorem that tells you that knowing the kernels of the Laplacian tells you also information about the topology. And I gave you two examples of Morse functions, one with more critical cells than the other. And we want to count them all. But then we go to the general version of the talk. That is, we are going to do this for simplicial complexes. So what is a simplicial complex? You can imagine just as a set theoretical definition of a simplicial complex. You just take the numbers 1, 2 until n, and then you take a collection of subsets of that set that is closed under taking subsets. Okay, so you could imagine that a graph itself is a simplicial complex because you can have edges being as subsets of two elements, but every subset has the vertices that are the endpoints. So the elements of a simplicial complex are called cells or simplices. And we can associate something depending on the size of the set will be the dimension. So I think this is very natural to define. And we define what a phase is for a simplicial complex, that is being a proper subset. That also induces a partial order on the number of on the set of simplices of a simplicial complex. Okay, so now we saw two examples. I didn't define them. I didn't define what a Morse function is, and this always intimidates people when you define a discrete Morse function because it's given by some sort of a cardinality condition, and it's actually two conditions. But remember what we said at the beginning of the talk. We said a Morse function is basically telling you that if you are changing the dimension, you are changing the value. And if you change it in a controlled way. So if we read the definition is, if you pick a cell of certain dimension, you're looking at the different cells for which sigma is smaller than tau. Remember that this poset is given by being a phase. So you are looking for all the cells for which sigma is a phase, and you are considering this condition, so sort of like a monotonic condition, and this set has to be either empty or it has one element. And then this condition also goes in the other direction. So if you now consider all the phases of the particular cell that I gave you, the number of cells that have this condition is also bounded. It's either 0 or 1. Okay, so without any motivation looks weird, but now I think we see that at least we have two examples. Yes?
So case of P, maybe I missed the last point from the previous.
This one?
These are the cells of size.
Of the dimension P minus 1, that means of size P, like it has a set. Yes.
And the inequality from sigma less than tau is that there are subsets?
That is a phase. Yeah, that is a sub. Yeah. So being a phase is this one. And then this one is actually the numerical inequality. So yeah, it could be confusing a little bit. But all right. Any questions about it? So this is a discrete Morse function, and you define a critical cell if this number is actually 0. So if it's an empty. So if this set in which things happen is actually empty, that will make a cell critical. Okay, for example, in the picture, you see another example of a discrete Morse function on a simplicial complex that has a bunch of, I didn't count how many vertices we have. We have a lot. We have also several edges here, 1, 2, 3, 4, 5, 6, 7, 8, I think. And we have 1, 2 cell that is that phase. And you decorate those cells with numbers. And those numbers have to satisfy the two conditions that I gave. Now, you can construct a gradient of a discrete Morse function on a simplicial set by saying, well, you are changing it's a phase, so that means that there is this condition on the dimension, and you are actually decreasing the value. So you for example, if you are in a graph, you are going down to a sink, so that will give you the direction of the arrows. So here is kind of a systematic way to construct what topologists call the Morse complex. So you want to make a hierarchy or a poset for cells and relate them by kind of going with an arrow. So here we have the number of these are the vertices. So 1, 2, 3, 4, 5, 6, 7. So this complex has 7 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges. 1, 2 cell, and you see these 3 edges are corresponding to these 3 edges. And then I would like to put the flows. So these are just this is just the poset by being a phase that I think in combinatorics has a name. What is the name of this? Is this the phase poset? Okay, so this is.
And what do you mean by flow, like arrows?
Arrows, yes. Now I want to like what we define as a gradient will tell you a direction, like this direction. So I will decorate this. So I will select the cells in which there's actually a flow. The rest are going to be critical because there's no flow, and I will just tell the direction in which the function changes. So maybe we can see this one, like the upper part of this one. So can someone identify what is that flow? So we have 13, 13, 20, 18. So I'm going from 20 to 18 down. Well, I go, it goes up there, but yes. So one chooses a direction and then one becomes consistent. But in this case, we always go down. So it goes from 20 to 18. So it goes in the direction of that phase. Okay, and I think that's related with that comment on the acyclic matrix. That is, if you were to count these discrete gradient vector fields, so things that actually have certain property, that is, you don't have cycles, that is a hard problem. That's hard to compute. And you want also to have a tight number of cells. So that was studied before. Yes.
I'm just sorry. So is there any requirement on how many of the edges you need to orient actually?
That's a good question. So this is actually bounded by the Morse inequality. So there is some topological conditions on how many things are critical. So you could not have things that violate this one. And then once you have them, then the question is, okay, can you orient the complement? Yes. So the numbers have certain conditions that are bounded by topology. And this is the example. So this is an example in which we had, maybe this is related to your comment. So here we have 1, 2, 3, 4 critical edges. We have 2 critical vertices. This is and this is how the gradient vector field looks like. So you look at the complement of the cells and see how you orient them. So give them a flow. Okay, so this is the story of how to define critical cells on a simplicial complex given a Morse function. Now I'm going to tell you the story of a Laplacian. So when you have a complex, you have this operator that is called the boundary operator. Like we saw it in the pre-talk, is the incidence. So it goes from edges to vertices. But you can do it in more generality. If you have an oriented simplicial complex, there's an analog of the incidence. It just, well, there are many more. It's not just one operator. Then you can define the Laplacian that is actually defined as composing the boundary with its transpose. So there's and remember we had the discussion before, which one should we use? So you can choose one direction and just make sure that whatever you are at the end of the complex, you don't say like trivial things in which that Laplacian is 0. So once you are in those endpoints, you can also choose the other direction. But this is a choice. You can define an operator, a matrix, on each level of the cell complex that is defined as composing these 2 operators.
So to calculate the matrices for like the deltas, I would look at the incidences,
Yes. So if you were on the case of when the complex is a graph, just compute the incidence and then compute the transpose and just multiply. If you have a higher dimensional simplicial complex, it's a bit more complicated, but the idea is if you have an orientation that induces an incidence, and then you can just do the same. Okay, so now it comes to back to the one-dimensional case. We were interested when we were working with Andrew in his thesis. Can we count this number of discrete Morse functions? And the observation is yes, we can. Realizing this observation, that is, if I basically have a discrete vector field, there is a correspondence between this discrete vector field and rooted forests. So basically, if I remove the critical cells, it can be disconnected, but the conditions of being Morse tells you that you cannot have cycles. So whatever you have left with is something that has no cycles, and it has some directions. So then it was natural to think that what you're actually being left with is a rooted forest, and it turns out to be true. So then you can define this number, mk gamma, that is the number of gradients on a graph that has k many critical edges. So it's the counting problem that we want to solve. So fortunately, there is a classic theorem by Biggs. Yes.
Maybe just one.
Oh.
So your critical vertices end of your slide being the roots of your forest.
Right. These are like the sinks. Yeah, exactly. Yes, that's right. And those are the roots. So if you have a discrete Morse function, basically the short computation is that critical vertices become sinks of like the roots of the forest. And there's a theorem that actually tells, like a classical theorem that tells you that the Laplacian helps you to count those numbers. So if you take the characteristic polynomial of the Laplacian, like the usual graph Laplacian, I think we called it delta 1 in our in the pre-talk, then the coefficients of the Laplacian count the number of forests having exactly how many edges.
When you say vertices about forests, essentially forests, you root all of the trees.
You root all of the trees. Yes, sorry. Yes, that's, I think I forgot to define what rooted forest is. Yes, that's right. Which is nice, which is actually tells you that there's a connection. Now we use this classical theorem to answer our problem for the graphs.
There's the identity matrix, not the incidence matrix.
This I is the identity, and it's different from this I. Yes. All right. So then just, I mean, assembling the things together leads to the result that just considering the characteristic polynomial of the Laplacian will give you the number of this, the number of gradient vector fields for Morse functions. All right. So this is, maybe you have to remove tab here. So I just wanted to give you an example, like the power of Biggs theorem applied to discrete Morse theory. Take C4, like a cycle with 4 vertices. I think we are able to compute this. This is the Laplacian for C4. We compute the characteristic polynomial, looks like this. And then we separate the gradient vector fields by the number of critical edges. So here it has only 1 critical edge. Here you have 2 critical edges. Here you have 3 critical edges. Here there are no critical, everything is critical. So this one, for example, is the one that we saw in the pre-talk, where you put 0 in vertices and 1 in edges. This is like this is the most critical Morse function. And there are tighter ones. So there are ones that are more, like they fit with the Morse inequalities, and they are actually equalities. And this is the whole kind of zoo of Morse functions that you have for C4. So I think that was nice for Andrew's thesis. So we were very happy, like, okay, so we understand graphs. But of course, there's a natural question that is, can we do this in higher dimensions? So is there a similar result for higher dimensional simplicial complexes? So then one can define the same thing, right? We can count the gradients on a simplicial complex by counting the number of critical cells. Instead of edges, now you have arbitrary cells. So a natural conjecture was this. So you can focus on the Laplacian on each level of the simplicial complex, compute the Laplacian there, compute the characteristic polynomial, cross your fingers, and hope that you get the number of gradient vector fields with that number of critical.
So I guess that's the definition of this.
ML?
Yeah.
So K is the simplicial complex. L is a fixed index. So the critical cells is that number. So you're counting like the critical cell. And D is a particular dimension that you are considering in here. Because now you can go from sector to sector of the whole complex. So there's a bunch of dimensions there. So that was the conjecture. The conjecture is false. So this is not true in general for simplicial complexes. But if they are simplicial complexes that come from orientable manifolds or oriented manifolds, then it works. So like if it comes from like triangulations. So like this. So if your simplicial complex is like, for example, just some triangulation of a good-looking space, then things work fine. And this is a remark. I'm sorry, I'm not an expert in matrix, but the way that one can extrapolate the notion of acyclic matchings or forests in higher dimensions, I think that the natural language is the language of matrix. So one can define spanning trees, for example, using the columns of the incidence matrix. And that's going to be like your notion of independence. So we follow the work of Bernardi and Clevans. Is that the right way to pronounce? Clevans.
Caroline.
Caroline. Okay, thank you. And then it's basically, there's a very cool extension of the matrix tree theorem that you learn in graph theory for graphs for these kind of higher dimensional objects. That is basically the characteristic polynomial for these D Laplacians, then we have a simplicial complex, is counting, so that there is a sum that you are doing over rooted forests of certain coefficients. So there's a weight that you associate in the characteristic polynomial. And this weight, this HD FR squared, is related to the topology that you have on your simplicial complex. So it could be a little bit more involved if you want. I mean, it's not a direct extension of the matrix tree theorem, but the important takeaway is that you have a sum over rooted forests. And if you would do the usual kind of version of the matrix tree theorem, is precisely the matrix tree. So this fits with the one-dimensional version. So here is the theorem that we worked with Andrew, is that if you have a d-dimensional simplicial complex, then and then you have a Morse function that induces this gradient vector field, then you can consider the set of non-critical D cells, and R is the set of criticals D minus 1 cells. So the red things that we drew for the graphs. Remember that the vertices were sinks, so you can do the same thing for simplicial complexes. So you have non-critical and critical. And if F is what is called torsion-free, that is a topological condition, that it's basically related to some homology groups with coefficients in Z mod 2, then it's a rooted forest. Not all the pairs of F and R will give you like Clevans and Bernardi's version of rooted forest, but if we have this condition, then it works. It's not an FNL data. That's basically the problem for us to have, like, for example, non-orientable manifolds and do this kind of triangulation. They don't give us like the right form of we couldn't use the theorem, so because of distortion. And this is actually the case. So unlike with graphs, this is not a one-to-one correspondence. So for graphs, they have the dimension is low enough that you can actually produce out of any rooted forest, you can produce a gradient vector field. But it doesn't work for things that are like the Mobius band over here, or this type of simplicial complex that has some kind of interesting topology. This is imagine like two tetrahedron glued together, and you also include the equator. So the equator is also a face. So this is a weird configuration of cells for which this is not a one-to-one correspondence. So then the question is what is the correspondence? If it's not everything, so what can we consider as some sort of like a correspondence between these kind of rooted forests in the Morse context? So this is a construction that is called it comes from people working on simplicial complexes. It's called F simplicially collapses to R. So I can give you an example of a simplicial collapse, but that is, if you have a graph, let me just try to erase. If you have a graph, you can simplicity collapse leaves that don't change the topology. So if you have K3 with antennas, you can simplicity collapse them. You didn't change the topology. So there's a higher dimensional version of a simplicial collapse in which you are considering something that are called free faces, and then you use this kind of method to remove them without changing the topology. So the proof, well, it's a little bit technical that direction. So given a set of non-critical and critical cells, do we have the condition that F simplicity collapses to R? It's a little bit, you have to use the actual conditions, the two equations, the inequalities that I gave you defining what a Morse function is, a bit more technical. But the other one is kind of a nice kind of combinatorial thing that is basically you have to fill out. So if you start with a simplicial collapse, you could imagine that I have to do like the reverse steps, and you just realize that there's never a problem. Like you can always just follow the arrows, and that will kind of produce for you a set of non-critical cells and a set of critical cells. So it's kind of like reverse engineering. Just follow the arrows.
How did you go to the fourth dimension?
I kind of feel the so this,
Oh, okay, your question.
yeah. So it's yes. Yes, yeah, I didn't say that. Yes, and then you have this. So this is the last step in which you have the critical locus of the function, like critical cells, and then you have all the directions of the gradient. So it's kind of like the inverse of simplicial collapse, filling horns. And then, well, if you have something that corresponds to a gradient, then you don't have distortion terms from Clevans and Bernard. So it kind of fits with what it was known in the literature. So we didn't break the laws of mathematics, like proving something wrong. So this was already there in certain way for these things with torsion. So we just realized that, well, so if you have this condition, then things are fine. So then the result can be phrased as follows. So if you have an orientable D-manifold, and then you have a rooted forest, then F simplically collapses onto R. So that means that when you have these triangulations or kind of simplicial decompositions of nice manifolds, you don't have these problems or the distortion kind of issues. And then, well, as I just mentioned, so if K appears as a triangulation, then we can actually compute the number of gradient fields using the expected conjecture, that is using the characteristic polynomial of these deltas. Now, how much time do I have, sorry? And
Plenty of time.
okay. So are there any questions? Maybe I can pause 1 second.
So when the Clevans, the Bernard result had a square, the coefficient was H2.
Yes, a square. Yes.
So how did that become the number? So that's equal to a square. That number is equal to
Oh, but yeah, remember that the sum runs, the two sums run over different things. So the sum of Clevans, put it, sorry, where is, did I already? No, I think I went, sorry. Yeah, so you regroup the sum in which, but yeah, you could get like a bunch of ones, yes. But they're like,
so the coefficients of these MLs are
yes.
also squares.
There's some, so they're just positive numbers. They are numbers that in
In
the,
this case, the torsion is 1 for you, right?
yes,
That's
the-
okay.
yes. And then, yes,
The h squares is just 1.
right. Okay, sorry. Now I went.
It is the sum of squares, that's the sum of 1.
They're the sum of 1 squares. So now the question is what happens when you have things that are non-orientable? So, well, first observation is that this doesn't work. So we found counterexamples in which you compute the characteristic polynomial, you see the coefficients, they don't match with the number of gradient vector fields. So, so if it doesn't hold, there's a way to compute the error. So the error is actually computed by this kind of torsion type terms, that is this kind of squares. So let's see an example. So if you have the Mobius strip, it's very, this was a bit weird for us because the numbers are actually almost an exact match for the number of discrete vector fields and the actual numbers, the coefficients. They match all of them except for this one, that the difference is 4. So this 4 comes from this type of possible kind of assignments of flows, but remember that this is a Mobius band. So when you glue them together, you may encounter a cycle, and that's something that you don't want. But remember that we want something that looks like acyclic matchings. The same thing happens when you have this bi-pyramid with an equatorial. So same problem. So we computed the characteristic polynomial. We counted the number of gradient fields, almost a perfect match except this coefficient. So there's a difference of 6 that accounts as how you can cyclically permute labels around the equator. So it's not a perfect matching. So there's some topological obstructions to have a nice theorem that is like it works cleanly. But the good thing is that there is at least a control of why it went wrong. So it went wrong because of this orientation condition. And now we can ask the question that is also natural for mathematicians. So if something fails, what is the set of things that fail? So is it just because of the orientation, or is there something else that we are missing? Are there like some weird complexes for which we still have something in between? So this is basically the question is and we call them regressive. So simplicial complex is regressive if all of its rooted forests contract onto their root. So you have like this kind of nice condition. The question is, what classes of simplicial complexes have this property? So can we characterize them all? Is it just being orientable, or is there something that we are missing? So that's basically the question. What can we do to a regressive simplicial? So that is still regressive. Can we like glue them? Can we take the product? So I think there are still some open questions there. Can this help in any way for real life mathematics? Like, can we help like making computations faster now that we can count the number of discrete vector fields? So let's say you have the number of characteristics, you have the characteristic polynomial that should be something that you can do relatively fast. Can we just assist, for example, people working in topological data analysis or whatever discrete Morse theory appears? Or for example, can you help to make faster computations for acyclic matching that it was like NP hard?
Sorry, what's chunk?
I think these are just the abbreviations of the algorithms, C, home, P, and persons. So I think these are just some algorithms in order to compute acyclic matchings.
The persons group has a better idea. So I would trust someone.
Yes, actually, this came from a talk. So someone was asking like, oh, so could you use this to like make more efficient computation? So, but again, I'm not familiar with like the algorithms to compute optimal matchings. And how does this generalize? So can we talk about this type of counting for polytopes, for example, or things that have more interesting geometry and not just the topology? Yeah, so this, or can we, for example, have an interpretation of homotopy groups, like something that is more other types of invariants for manifolds. So this goes towards algebraic Morse theory. So these are kind of open directions of things that maybe we could think in the future. And I think that's all. So thank you so much.
Question for you?
Sorry, can we just before you said that the main theorem, like a few slides before you said that we don't have a good theorem in general, but we do have a correction.
Yes.
So do you have like an explicit theorem that is analogous to the equivalence and all theorem? It just doesn't behave that. Like, do you have an explicit formula for the characteristic polynomial in any case, even if it's not just that?
Oh, that's a good, yeah. So that's related with this kind of characterizing these regressive complexes. So if they come from triangulations of manifolds, then you can say, oh, this is related to being non-orientable. But we also know that there are some simplicial complexes there that, you know, like might have this kind of property without coming from this triangulation. So.
No, but I'm not asking for which ones it would work and include it. I'm saying, is there a formula that doesn't look as good as the sum of those things?
Oh, but still,
maybe some with some other coefficient.
I think the closest is what we did is finding the error. Oh, sorry. So this, yeah, this is the best. Like this is basically controlling the difference is given by these squares.
So then the complete formula would be the sum of the quantity of the set
plus this.
those
Yes.
squares.
Yes.
Huh. Okay.
Yes. Yeah. So yeah, we have this.
One polynomial, it's not equal, but coefficient by coefficient is less than or equal.
Yes. So there's a, yeah, exactly. So these are positive numbers. So I think the best result is that there's an inequality, coefficient by coefficient, and well, this. So.
Okay, I also had a few more. So like the chromatic polynomial,
Yes.
right, is cool because you can count a cyclic orientation by evaluating the chromatic polynomial at -1.
Yes.
Do you have any situation where the graphic news of something can appear after a similar evaluation?
That's a very good question, and I think that would be great to have. I mean, the answer is there should be something that basically doing something like the chromatic polynomial or some variation of it produces exactly this type of, yeah. But I think the question that people ask is there a Morse function that produces this type of numbers? Like some question is like, okay, you have some numbers and you know that these numbers behave like the Euler characteristic of a complex. The question is, can you build the complex? Like, can you find a function for which the critical cells match with your problem? So that would be maybe the question to ask that is related to your question, but I don't have an answer. so yeah.
Other questions for you, Ivan? I checked in Zoom. So it's just one. So this holds only for these like triangle. This holds for the triangle. They have to be triangulations, or the,
Yes.
the
So triangulation in the higher dimensional sense. So it's just, yeah. So simplicial complexes that approximate a manifold. Like this is a triangulation for the Mobius line.
Okay, has one more. Also, the matrix forest theorem, it has a weighted version,
Yes.
but in a different sort of way than the equivalence weights, right? Because for each edge, you assign your own parameter from A to J,
Yeah.
and then the answer is the sum over for each tree or for each forest, you have the product of the weights.
Yes.
Would there be something?
That's another great question. So I think a natural direction is to do like weighted graphs. You know, like there are some weights and there are weighted Laplacians that are similar to what you're doing. I wouldn't know exactly what is the discrete Morse interpretation of having a weighted in that sense. But yeah, maybe that's something worth exploring. Like, can we have a weighted version like in which like one cell weight is more important than another? I feel like Morse theory treats all the steps in the same way. Like you could try to mimic something that gives you certain relevance of some cells over others.
But it's interesting because it's like a statistic as well. It's not that we care about the particular value of the weight, it's that we have
Right, like around,
threshold
yes,
economics.
absolutely. And that could be like something that maybe from the point of view of topology makes sense. Like, yeah.
Thank you very much.
Thank you.